the ordinary setting with writing down the propagator. So when we have a gauge theory, we need to fix a gauge, and the choice of a gauge gets you a propagator. So I'm going to explain, firstly, how that works in the BV setting. So we'll work with the simplest example. Where our fields look like forms on some three-manifold tensor Lie algebra. This shift by 1. The shift by 1 is to put one forms, which is your gauge field, in degree 0. And we have the Renormalization. And this is defined for an arbitrary field. And just to remind you, like if this field was in degree goes to number 0, so it was one form, this would be literally the Renormalization. But including fields of mixed degrees allows us to capture all the BV action, including the terms with the ghosts, the ghosts and the antifields, and so on and so on. So how are we supposed to integrate this? So if you remember, we saw that if we have an odd symplectic manifold, and with the solution of the quantum master equation on it, and then we should integrate that over a Lagrangian inside your manifold, half-dimensional subspace. And the quantum master equation will tell you that the answer does not depend on the Lagrangian we choose. So in this BV setting, the way you gauge fix is you choose a Lagrangian inside this space. Lagrangian in the other sense of Lagrangian. And then we do the integral. And we do this integral over the Lagrangian. And we require for this to be a nice Gaussian integral, this kinetic term must be a non-degenerate quadratic form. So alpha d alpha is non-degenerate. Okay. Okay. So how are we going to try to arrange to get something like this? Well, it turns out we can get this very nicely using Hodge theory. There's an operator d star from omega k of any manifold to omega k minus 1 of any manifold, and local coordinates, it looks something like d star. It depends on the metric. So this is just ordinary derivative, and this removes a dxj from a k form. So it looks something like this in local coordinates. And it's, I'm sure most people are familiar with it. It's a standard thing, and you can read about it in geometry textbooks. It can be written in terms of the Hodge star as star e star.
E star is star e star?
We also have the Hodge-Laplacian, which is the anti-commutator. And Hodge theory tells us that the space of forms splits up in a very nice way if M is a compact manifold. So forms in M as three pieces: the image of D star, the image of D, and in the middle there's a harmonic forms, which is the kernel of the Laplacian. So harmonic, it really means if you work in local coordinates, the coefficients look like they're harmonic. So this space of harmonic forms is isomorphic to the cohomology of M, and it's finite dimensional. So and a standard Hodge theory observation is that every form, every cohomology class has a unique harmonic length. Okay, so why are we doing this? So we have this decomposition to three pieces. And we know that these guys represent the cohomology. So somehow, these two pieces must cancel when we take cohomology. And what happens is that the operator D is an isomorphism going that way, and D star is an isomorphism going that way. So that's great. That tells us that on this subspace, we have a chance of our quadratic form being non-degenerate because nothing in this subspace is in the kernel of B. What's slightly annoying is that, we wanted to integrate over a Lagrangian. So if we ignore the harmonic stuff, this is indeed a Lagrangian. But we don't really have any chance of getting a non-degenerate quadratic form on the harmonic stuff because that's the real modes of your theory. It represents massless things. So what we'll do instead is we'll just integrate over the massive things. And later, at some unspecified time, imagine we will do a finite dimensional integral over this manifold. So we will integrate over M D star, which is inside of MD plus MD star. And this is the same as the orthogonal complement to the harmonics. And we should be left with some kind of effective measure on the space of solutions to the equations of motion. In this space, the tangent space of this is like something like H tensor G shape. So we're not going to worry too much about how will we actually perform that integral over the zero modes. That's left for another day. If you really are worried about it, you're probably not. You can carefully engineer that so that you have some gauge field. There's no zero modes in this sense. Okay, any questions? Okay, so let's see if we can understand the propagator. So if I take my field alpha to be in MD star tensor G of 1, then integral of alpha is a non-degenerate quadratic form. So it's reasonable to perform the path integral over this subspace. So to be clear, like the gauge we're using is like the most standard one, the Lorentz gauge. So if alpha is a one form, then locally then, well, because d star squared is 0, d star of alpha sum d ij state alpha I is 0. So this condition is just the most standard Lorentz gauge condition. I don't know if there's a T or not. Okay, so how are we going to find the propagator? Well, what we need to do is, so in the case of, like say, a scalar field theory, we saw that it was really useful to write the propagator as an integral of the heat kernel. So you can do the same thing here. There's like a kind of Dorama version of the heat kernel, and we'll write the propagator as an integral of that. So we define subelement k p of x, y, which is the 3 form on M cross M. So, and locally, well, let's see. So that, firstly, it satisfies the heat equation. And secondly, it has the initial condition, k is 0 of x, y, is the delta function of x equals y. And it's natural in differential geometry to view the delta function as being a 3 form because it's codimension 3. So locally, you can expand kt xy is some kind of sum. It has some components which are, say, we're summing over these multi-indices. It might have a 0 form times a 3 form, a 1 form times a 2 form, 2 form times a 1 form, 3 times 0 form, and so on. And these conditions mean that these guys satisfy some differential equations, which fix them uniquely. If you were to work with the flat metric, it's very simple. And the kt looks like t to the minus x minus y squared over t to the minus 3 over 2, dx1 minus dx dy, dx1 minus y1, dx2 minus y2, dx3 minus y3. This is the expression in flat coordinates, so it's just the scalar heat kernel times something which only depends on the distance, the difference between these points. And in particular, you can check that if t goes to 0, this becomes a delta function. This gives you the kind of correct form contribution. So here's a few other properties this will satisfy. Everything okay? So as you can kind of see pretty clearly here, these equations will imply it satisfies similar equations with the y instead. So del x kt is equal to del y kt. But also, the Dorama operator on both variables, kt is equal to 0. You see this equation, so d by dt, hi, sorry, are you feeling okay? Is equal to x plus dy, Laplacian on x, kt. So we can bring the Laplacian in the x variable commutes, of course, with the y Dorama operator, but also with the x Dorama operator, because this is because the commutator of dd star b is equal to 0, because if I do this commutator, I pick up a d squared. So the point is, if I apply the Dorama operator, I get something which itself satisfies the heat equation. But it satisfies the heat equation with the initial conditions being, while if this is 0, it's a delta function, which is a closed form. The initial conditions being 0. So something that satisfies the heat equation with initial condition 0 has to be 0. So everybody feel you have some understanding of the heat kernel with coefficients and forms? So this is like a super general thing. There's one for the Dot-Bowl complex. Anytime you have an elliptic equation, you can write down some kind of heat kernel.
Does it have to be first or second order?
Yeah, it has to be first or second order. I mean, so let's see, to be more precise. So we write down a heat equation. It's d by dt is equal to something times this guy. What do you need to be able to find a solution? You need that this guy looks like the Laplacian. So that means it's a second order operator whose leading term is the Laplacian, but there could be also first order terms which can be pretty general, and zeroth order terms, which can also be pretty general.
So, yeah, non-uniform coupling, it could be something like the reduced Garrett condition to the Laplace operator.
Yes, you could have a zeroth order term there too. That would be fine.
But presumably, this strategy for gauging is quite work, I guess, in that case.
No, I think actually that's happening implicitly, because if you're on a curved manifold and you look at the Hodge Laplacian, it is not the scalar Laplacian. They differ by exactly the weak scalar.
I see.
For example, on top forms. So if you calculate BD star acting on an n form and compare it to the scalar Laplacian, there's a difference.
I see.
It's kind of when Weizenbach forming. Any other questions? Okay, so we want to calculate the propagator. So what do? We just say the claim is that the propagator P, which should be an M D star tensored with M D star, is Pxy equal to the integral from 0 to infinity of d star, the x variable, times the heat kernel xy. So we want this to, so let's check the key property. So key properties. So let's, firstly, we want d star x propagator y0 and d star y, the propagator of x y equals 0. So I'm going to not be too careful about the difference between being in MD star and being in the kernel of D star. They differ by some finite dimensional space of harmonics, which is not so. So we want it to satisfy age fixing condition in each variable. Clearly it satisfies it in the first variable, d star squared is 0. You can check it also satisfies it in the second variable. We're not going to, it's not too difficult by a similar argument what we did there. This is actually not so bad. And more importantly, if it takes some guy alpha, which is in, say, the image of d star, then you want the integral b in the x variable give you back alpha. So normally, if this was a scalar field theory, you would say a propagator is something that when I integrate it against a function and then apply the Laplacian in the other variable, you get back what I started. But now we're not using the Laplacian anymore because our kinetic term just has the Dorama. So I say by the Dorama operator, I should get back what I started. So what we need to do is check that this guy satisfies that. How do we check that? We just plug in an alpha and just verify. E in the x variable of integral 0 to infinity d star in the x variable e kernel x y wedged with alpha of y. And here we're integrating over y as well. So it's the integral 0 to infinity, integral over y dx plus commutator of the x, the star of x, minus the star x dx. Now, this is of course the Laplacian. And this is a closed form. So d applied to the x variable is applied to here is minus d. Oh, I hope I'm not going to get myself confused about something at this point. Let's see. Again, a seat of the pants preparation method is its problems. So let's just keep that extra term around for now. Figure it out in a minute. So. Minus infinity integral y del t okay. So this is the term, this is the good term. So I've used the heat equation to replace this guy by a del t. This is the good term because now I can integrate over the t variable, and I produce, because it's a total derivative at things from 0 and infinity. So this term here produces two terms. One is the heat kernel at 0, which is the delta function of x equals y, and heat kernel at infinity, which gives projection onto harmonics. Now, since we're assuming that alpha doesn't touch the 0 modes, this will be 0 for alpha. Okay, so this term just gives us the integral of the delta function of x, y, alpha of y, and that's alpha of x. That's great. Now we have this problematic term. Let me think for a second how to deal with this one. So what I want to say is that, why am I confused about this? Give me a second to think about it.
Is that just 0?
What's that?
Is that just 0?
It should be 0, but I'm being a bit...
dx, because that equation dx plus dy kt equals to 0. So dx kt equals to minus dy kt.
Yes.
And alpha is in the image of d, so d of alpha is 0, so it's just dy of k.
That's the point. Alpha is in the image of d star, though. Right, alpha should be in the image of d star, not the image of d, and that's the point I got confused at. I agree with your argument at that point. Sorry. Yeah, it's something really stupid about like using the fact that alpha is in the image of B star. Almost. Yeah, I'll give up. Let me write it over here, because I think I can. Sorry, we got. So, first thing, it should be easy to see. This is the standard convolution of alpha of y is alpha of x. So that the integral E kernel is like the Laplacian inverse. So now we're saying, so what is D star times Laplacian inverse? What is D of D star times Laplacian inverse alpha? This is Laplacian minus star E times Laplacian minus alpha. Oh, why am I so confused by this? It should be completely trivial, but here's another way to say it. So this breaks up into eigenspaces of the Laplacian. This breaks up into eigenspaces of the Laplacian. And this is B. And the commutator is the eigen. So I take here. I take something here. I have
Is it possible that we want the other condition to hold? Put D first and then take the propagator, get that identity? Is that not good?
That would be the right one. Yeah. That's the condition. Yeah, that's the issue. Sorry about that. Yeah. Okay. So then, yeah. So like B star X, B X Y, B Y alpha is equal to alpha. So you want it to be left inverse versus a right inverse, and this seems to work better, right?
I think so.
Yeah, because by integration by parts, we can move this over here. So this is equal to, yeah, integral B star X minus integral B star X. Dy A T X Y alpha, which is plus B star X. X so we get okay, so this is alpha plus stuff in MD, which we shouldn't want. So I can move this out, I get alpha plus things in MD, which I can't possibly get because it's manifestly not in MD, it's B star. This is really alpha plus harmonic stuff. So. Does this make any sense? Sorry, it's a bit dubious. But
Can you repeat this last?
yeah, so let me. Sorry for fusion. So, integral of B star X over P and Y, A T X Y, B Y alpha. So by integration by parts, I bring this over there to an X. I bring this over there, I can this guy, and then I make it act on the X variable. That's plus or minus integral B star X dx A T X Y alpha. So this is plus or minus the integral of the Laplacian kp alpha plus stuff things in MD, which we can't possibly have. So I think what's going on is, let's write this stuff in MD. So the stuff in MD looks like the integral of dx b star x ktxy alpha y. This stuff here, this is the things we know can't contribute. Well, another way to see why they can't contribute is, although this is not literally the Dorama operator, there's similar integration by parts rules that allows me to transfer this guy to act on the y variable of here and then make it integrate by parts to act over there. That will be 0 because it's in the kernel of B star. Okay, so sorry for the confusion. We could have said this originally too if I wasn't so confused. Yeah, okay, so this is actually, this one is not the good way to do it. So Eugene is right. We're supposed to apply this operator to g of something. See, it works the other way around. So this is bad. That was the origin of the mistake. So the good one is this guy. This guy is equal to 0 using that b star x plus or minus b star y p is equal to 0, and b star y alpha is equal to 0, and integration by parts. So people reasonably happy with that? And sorry for the confusion. Okay, so now we have a propagator. We can write out the same kind of Feynman rules as we did before. So we can also define a regularized propagator. We can use the same Feynman rules. So at a vertex, we put integral alpha cubed, and an edge, we put this guy, and then we can define something by WP epsilon L be the sum over graphs, connected graphs of h bar times the number of loops times the Feynman amplitude. And the same statements we did before apply in this context too. So the amplitude is a function of a field alpha. Now, despite our gauge fixing, there's nothing forcing us to have the background field be in MD star, just be anywhere. So exactly like before, there's going to exist a unique set of counter terms which are purely singular, as a function of epsilon, so that once I subtract off the counter terms, this has an epsilon to 0 limit. So we don't really do this explicitly, work out some of these explicitly stage, but this is just the same thing as before. So we can ask, why does this propagator and this formalism help us with understanding the problem of defining the quantum master equation? So that's because that's because of an important homological feature of the propagator. So if we view this propagator in just forms on M cross M, so it's a two form without imposing any gauge fixing condition. It's kind of key formula. The Dorama operator on both variables of the propagator is the E kernel times epsilon. It's the difference between the two heat kernels. So why is this? So this is going to follow by the same kind of argument that I messed up a few minutes ago. It's an easier one. So I hopefully won't mess this one up quite as badly. The integral E star x E x y integral onto L of Laplacian in the x variable minus E star x dx, but also minus E star x y, because dy and d star x anti-commute with each other. So I pick up a minus sign and pass each other. That's E kernel y. And these two terms cancel because it's closed. So I just get this term. Which is what we want. So this equation is going to allow us to understand a compatibility between the orgy flow, which is given by this kind of sum over graphs, and the quantum master equation. So to see this, so we say some interaction I satisfies scale L quantum master equation. So I put that makes if well the following I'll write it out diagrammatically. So the first term is the Dorama operator applied to I of L plus something like this. Okay, so what we're thinking of is this guy is a functional of some fields, so I can draw this one like this. I have my fields, and I'm summing over ways of applying the Dorama operator to each of those guys in turn. Then I have these two other terms where I put two of these guys and connect them by an edge with the kernel, or I have a self-edge with each. Now, if L is 0, this just literally is the quantum master equation. So we can think of this term here as some kind of bracket. And this term here is some kind of dV Laplacian. So what have we done? We've taken we had this problematic quantum master equation which involved the delta function on the diagonal, and using that as on an edge. But that led to problems because it's too singular. Here we've modified it into something smooth. We get this effective quantum master. Any questions?
So how do you see that? I mean, this also looks like the RG flow equation.
It does. It's just the same as the infinitesimal orgy flow equation.
Right.
But the first term looks like the derivative with respect to L.
Oh, okay. Yeah. So
Yeah.
I see.
That's going to be like. But if you saw, what we're going to see is that the orgy flow equation takes you from solutions to these two equations for different values of L.
I see.
The orgy flows. And you can see that by looking at the infinitesimal orgy flow equation.
So there is also an RG flow equation involving an L derivative?
Involving which?
An L derivative?
The usual infinitesimal orgy flow equation involves the L derivative. What you should think of is that the L derivative is related to the Dorama operator on the L line. And this is related to the Dorama operator in the internal space.
I see.
Okay, so
So there is some statement then about what kind of course maybe you're thinking about here being, I don't know, different from what you're doing in the scalar field here?
it's really the same kind of thing.
I see.
So it's just we have this gate fix, and the things are in the kernel T star, and then we're doing that kind of coarse grading weighting fields.
Right. No, I just mean in the sense that the L derivative being replaced by the Dirac operator seems like there's something way more localized.
I see your point, but this is not literally the orgy flow equation.
I see.
So there's going to be a kind of compatibility between them,
I see.
which The one I can remember offhand is the non-infinitesimal one. So, well, we can derive the infinitesimal one afterwards by looking at it. So, lemma. If I have something which satisfies scale epsilon, one master equation, and then we apply the order to flow, this operator here is, so this is the thing, the integral of that, or infinitesimal order to flow equation. Then this satisfies the scale quantum master equation. So the proof is it's going to be just diagrammatic. So some sum over connected diagrams. Things like these kinds of expressions where every edge I have a p and every vertex I have an I. So what's going to happen if I apply the Dorama operator to every external I? Well, just by thinking about integration by parts, this is some big integral where I have some contributions coming from vertices and contributions coming from here. If I apply the Dorama operator to each external line, you can think of that as applying it to each vertex and to each edge. So B so this is sum. There's terms why I apply D to one of the vertices. Sorry, just one of them. There's also going to be terms where I apply D to one of the edges.
When you write that you mean, by that you mean D at each external
Yeah.
you apply.
Yeah, so what I'm using is that the thing I have a vertex is some multilinear operation, and I'm declaring that D of a multilinear operation on a cochain complex is the way it is in the dual of a cochain complex. I applied D on each input. So, I mean, there's something silly about I'm contracting a bunch of tensors, and contracting tensors is a cochain map. So applying D to the whole thing means I just apply D to the individual tensors. So the other terms are okay. But let's break this up into two pieces. Okay. So I either apply D to a vertex or I apply it to an edge. So D of vertex gives . this thing plus d of edge gives I get k epsilon KL and think of the difference between them, because that's what d of the propagator is. Now I have to sum everything up. Now, you can convince yourself, these two guys, that the d of a vertex ones, the k epsilon, they will just cancel. Because the ones for, say, d of a vertex, the result is a sum over all graphs with this special edge on which I place k epsilon. Whereas this guy, it's two sums, sum over a graph with a special edge on which I place k epsilon, and sum over graphs with a special edge on which I place kl. So these ones here, these just cancel with each other because they appear with different signs. And we're left with is that convincing? I know I didn't give all the details, but is it at least plausible? So, sum over connected graphs gamma plus one special edge of most of the time I'm going to put, you have the usual propagator, but this k epsilon will appear only on one edge. Sorry, that's not k epsilon, it's L. Now I think we're almost done because I have this KL, and if I snip it, I'm either left with two graphs or with one graph. So if I'm left with two graphs, well, each graph is the same kind of thing we did before with the same kind of propagator. Has this vertex, so either I'm breaking it up into two graphs, each of which looks like applying the orgy flow, or I have one graph which looks like I've applied the orgy flow. So we've concluded that applying the Dorama operator to this guy is the same as taking this guy, the sum of these two terms, where I have a KL in the middle. And I've done this by you apply it to every edge and vertex, making up this big sum. A bunch of the terms cancel, and these are the ones that don't cancel. Make sense? Now, yeah, I don't, off the top of my head, I'm having a bit of trouble remembering how the infinitesimal form of this will go. But, you could look at this and then differentiate it and see.
If this were Yang's theory, would you have the point mass equation with something like the Laplace equation?
Yeah, so that's a great question. So if it was not the simple topological theory, you have to work a little bit to figure out like what's the analog of this integral of the kernel and of V star. So there is an analog for Yang-Mills theory, but I only know how to do it when we write Yang-Mills in the first order formulation. And then there is something which looks just like that. The integral of the heat kernel with the D star, except there's some projection onto self-dual pieces. It's very simple. Any other questions? Yeah, I also don't know how to do this for gravity. You should be able to, but I just don't know a good gauge fix in this language.
Presumably you also want to go to the first order thing.
Yeah, exactly, yeah. But it gets pretty messy. Okay, so maybe we will stop there, and maybe next time I can explain how to do the Mills theory, and we'll talk about how you can try to solve problems.